Yeah, so today I'll tell you about a paper that we worked on recently at Riverlane, which is about quantum simulation of generalized Hubbard models. And this was a collaboration with researchers at the University of Copenhagen. So in particular, the first author on this paper is Andreas Jurbe-Smith. So Andreas is a PhD student in Gemma Solomon's group. And so he did a lot of the work that I'm going to be presenting today. So this paper is about trotter schemes for the Hubbard model. And so there have been a lot of quantum computing papers recently looking at the Hubbard model and showing that trotter schemes in particular are very efficient here. However, most of these schemes focus on the square-lattice Hubbard model. And so what we've done in this paper is take one of these schemes and generalize it to work firstly with arbitrary lattices, including frustrated lattices, but also to include more general interactions so that we can treat things like an extended Hubbard model and also something like a PPP model, which would have more relevance for chemistry. So in the first 20 minutes or so, I will give some motivation and a kind of general introduction to trotterization. And then in the rest of the talk, I'll speak about trotter schemes specifically for the Hubbard model and about the scheme that we introduced in this paper. So I just wanted to start by telling you about a paper that we put out at Riverlane a couple of years ago. So in this, we looked at quantum algorithms applied to pharmaceutical problems. So this is work done with Aztecs. The Aztecs gave us some molecule. And for this, we constructed various active spaces from 14 orbitals up to about 100 orbitals. And we looked at the cost for quantum phase estimation for this using two different approaches. Firstly, using trotterization, and then secondly, using qubitisation. And so some of the results are shown in this figure down here. So on the x-axis is the number of physical qubits. On the y-axis is the total runtime in days. And so the first thing is that trotterization is doing a lot worse than qubitisation here. So for something like a 42 active space, we estimate that to do a single shot of QPE, you'd need to run for something like 1,000 days. So qubitisation does a lot better, but still this is very expensive. So for the same active space, you still need to run for like at least several days. And the number of physical qubits using error correction will be like at least 1 million qubits. And then in the table on the right is the T-gate counts. And so apart from the smallest active space, you see that you need at least something like 1 billion non-Clifford gates to study this problem. So just to show a couple more examples from the literature, so there's been a large effort to cost various quantum algorithms, such as quantum phase estimation, for kind of interesting chemical examples. So these are two papers by Google and collaborators. So the figure on the right is for some cytochrome P450 enzymes, where they're looking at different active spaces of different sizes and looking at the number of Toffolis you need to perform a single shot of quantum phase estimation with qubitisation. So there are 3 different schemes here using single factorization, double factorization, or tensor hierarchy contraction. And so they show that the best scheme here is THC. But again, to look at something non-trivial with kind of 40 or 50 orbitals, you need again about 1 billion Toffolis. And then FeMoco has been another kind of classic case study. And so this is a table summarizing various results. So the top result is, again, using trotter methods, and they say you need something like 5 times 10 to the 30 Toffoli gates. And then over time, this has come down so that in this paper, they give an estimate of 5 times 10 to the 9. So this paper is a few years old now, and there have been improvements since then, but this is still roughly the kind of state of the art that you need kind of at least 1 million physical qubits and something like 1 billion non-Clifford gates to do something kind of industrially relevant or interesting.
What is the metric Toffoli count?
Yeah, so most of these costings are done in a specific QEC scheme. So we have to use quantum error correction to be able to get to the error rates that we need. And so in the standard QEC schemes that are often considered, the non-Clifford gates, T-gates, Toffolis are the most expensive because you need to consume some magic state, which is very expensive to create. Also, these usually assume a particular scheme proposed by Daniel Latinsky, so-called like Latinsky costing scheme, where basically all of the Clifford gates can be kind of moved to the end of the circuit. And so you just end up having to count the non-clippings. I mean, there are questions about how practical that will be in many situations. So in this talk, I'll be talking about early fault tolerance, and there we think that scheme is probably not relevant. And so in the future, we'll also want to count clipped gates, for example. But this is kind of the standard in the community. Yeah, so again, in this scheme, you usually just assume that you perform all of the gates in serial. And so things like parallelization are obviously important, but kind of this level of costing, you don't really think about, don't really worry about it too much. Okay, so now to look at a couple of papers for the Hubbard model. So there have been some recent papers that have shown that actually here you can do something interesting with kind of 10 to the 6 or 10 to the 7 non-clipped gates. So there are a couple of papers in particular that have been influential for us. So firstly, another paper by Google and collaborators. So in this paper, actually, they look at lots of different Hamiltonians, including electronic structure Hamiltonians, but I'm just focusing on the Hubbard model results here. So they look at 3 different trotter schemes, and they show that the best result, you can do something with about 10 to the 7 T gates. And then a paper a couple of years later by Earl Campbell, where he introduces another trotter scheme for the square-lattice Hubbard model, which is called Tile Trotterization or FLAP. And so here he finds that actually you can do something with around 1 million Toffoli gates in total. So this kind of regime of around 1 million operations is what is often referred to as early fault tolerance. And so at Riverlane, this is kind of an increasing focus for us. As you probably know, we work a lot in quantum error correction. We're trying to essentially build the QEC stack for an early fault tolerant quantum computer over the next few years. And so in our algorithms team where I work, this is becoming an increasing focus, asking what can we do with this device, what applications and algorithms are interesting in this regime. So just to give a bit more motivation, why is this sensible to look at for early fault tolerance? Firstly, why look at model systems? Many of these systems are very hard to simulate classically. In something like the Hubbard model, you can control the correlation strength. In contrast, if we look at pharmaceutical applications, for example, it's very difficult to find something which is truly strongly correlated. And this is where we expect a lot of the benefit to be for quantum computers. Quantum computers also have an infamous data loading problem where, like in your electronic structure Hamiltonian, you have n to the 4 terms. Just loading these into the quantum computer can be very expensive. For model Hamiltonians, this is obviously you have very few parameters, and so this is less of a worry. Why do I think trotterization is good in this regime? So firstly, in general, you don't need any ancilla qubits. The circuits are extremely simple, so they usually just consist of some layer of rotation gates plus a small number of Cliffords. So these are already run on NIST devices, right? So these are relatively simple circuits. They also can be very efficiently parallelized. And so trotter schemes have this nice property that they preserve the locality of the Hamiltonian. So for something like the Hubbard model, where each term acts on just 2 qubits at a time, this is preserved by the trotter scheme. And so if you have a sensible layout of qubits, you can kind of do many of these operations at the same time. And then lastly, a kind of obvious point, but these implement dynamics or time evolution, which is also considered to be a promising area for quantum advantage. Obviously, there are papers out there in the literature which argue that maybe there's no exponential advantage for ground state preparation, for example. But I think performing quantum dynamics is one of the more promising areas.
So,
yeah.
Doesn't T depth, Toffoli depth then become quite important?
Yeah, exactly. So the results that I was just showing, as I say, they just don't consider such things essentially. But yeah, if you want to actually start to think about how you'd run one of these algorithms on a real device, like an early fault-tolerant quantum computer, then yes, this does become important. And so this is one of the reasons that I'll be arguing that this is good for trotter schemes are good, and maybe qubitisation schemes are less good in this regime when you actually have to work out all of the circuits and how you'd implement it. So yes, in that case, the Toffoli depth is important, I think. And I guess the thing to say on like a fault-tolerant quantum computer, idling is as expensive as any other operation. So if you're just performing one gate and then all of the other qubits are just idling, then that is still a massive cost, and so you want to reduce that idling. Okay, so for the next few slides, I'll just give a kind of basic introduction to the idea of Hamiltonian simulation and trotterization in general. So as you probably know, the chemistry Hamiltonian that we're most interested in takes this kind of form. In terms of fermionic operators, to work with this on a quantum computer, we usually want to map it to Pauli's using something like a Jordan-Wigner transformation. So we can write this as a sum over Pj, where each Pj is some multi-qubit Pauli in general at qubits. So the problem that we want to solve, the problem of Hamiltonian simulation, is to find an algorithm to perform time evolution for this Hamiltonian, so to implement e to the minus IHT. And of course, the reason that this is non-trivial is on a quantum computer, whether we're working with physical qubits or logical qubits, there's a limited set of gates that we can implement. And so we have to try and compile everything down to those gates. And specifically, we're trying to find some unitary that I call S of t, which can be implemented efficiently and which minimizes this error. So this is our approximation S of t minus the exact evolution, and we want to minimize this norm. This norm is usually taken to be the spectral norm or the operator norm. And so trotterization is one way to approach this problem. This goes by different names in maths communities. These are sometimes called product formulas. In physics and chemistry, we tend to just call this trotterization. So the idea here is that we're going to split our Hamiltonian into some smaller number of parts, hj, such that we can perform time evolution for each of these parts, right? So we can't do time evolution for the whole thing, but for these smaller terms, we know how to implement this. So the simple example would be if each hj was just a Pauli, then we know how to implement e to the minus I Pauli t. And so there are lots of different product formulas. So the most well-known are the first order and the second order formulas. So the first order, we just implement each of the terms individually and take a product of all of these. In the second order, we run through all of the terms in one order and then run through them backwards, essentially. And it can be shown that the error in the spectral norm can be rigorously bounded. And so the first order formula has error that goes as t squared, and the second order formula goes as t cubed. And in general, there are recursion relations and ways to come up with even higher order formulas. These tend to be a lot more complicated, and I think they're less widely used. But in general, if you have a p order formula, then the error will go as t to the p plus 1. And importantly, there's also this prefactor WP, which I call the Trotter error norm. And this is related to the commutators of the individual terms. And so this is some nested commutator in the general case. And I think it's kind of important to point out this is just a bound. And so in some cases, the actual Trotter error is much less than this. And this is one of the problems working with Trotter methods, that trying to work out what the error is can be very difficult. So like qubitisation, you might say, is relatively easy to analyze, but very difficult to implement. The Trotter schemes are kind of the opposite. These are relatively easy to implement, but quite difficult to analyze. So in our paper, we'll just work with the second order formula. And so I just note that it can be written in the following way, which I'll be using later. Okay, so I've told you how to implement what we call a single Trotter step. But suppose we have some error that we want to reach epsilon. And suppose our Trotter approximation has a bigger error than this. Then what we can do is we can just split time into a smaller, into a number of steps. So we can take the full time evolution operator e to the minus IHT, perform it in r steps of t over r, and implement each of these with the product formula. And so if we look at the corresponding error, we need to replace t by t over r and multiply it by this factor of r because we're taking r steps. And if we just invert this equation is telling us if we have a target error epsilon, how many steps r do we need to take? And so this goes as the p fruit of our error norm, and it goes as 1 over the p fruit of epsilon. And the scaling in time is 1 plus 1 over p. So for any quantum algorithm, you need to run for at least order t. That is kind of the optimal. So these algorithms do not quite reach that optimal, but as you go to higher and higher orders, you can get closer and closer to order t scaling. And just to give a quick comparison between Trotter and so-called post-Trotter methods. So post-Trotter means things like qubitization. So query complexity just means the number of times I have to call the underlying oracle. So in Trotterization, this is the number of Trotter steps. In qubitization, this is the number of times that you have to call your block encoding, for example. So I've just told you what the query complexity is for Trotter. For qubitization, they can reach the following query complexity where this is actually optimal in both T and epsilon. So they're linear in T, and they have this log 1 over epsilon scaling in the error. However, the scaling in the system size depends on these three factors. And actually, in this case, Trotter methods can do better. So I'll show later that for the Hubbard model, this WP is actually order n. In particular, for local Hamiltonians, simple model Hamiltonians, this can be just order n, and so total scaling is like the p root of n. Whereas for qubitization, for example, this scaling depends on the one norm of the Hamiltonian, and so this will be at least order n. And so this is the opposite of the situation that I was showing on the first slide, where I said qubitization scales much better, and that is usually the case for kind of electronic structure Hamiltonians. But for these kind of model Hamiltonians, Trotter methods can do better. This is something that I hadn't realized kind of when I started this, so this is quite nice.
So I guess maybe you'll explain this later, but what's the intuition behind the fact that these local Hamiltonians have better scaling?
So I'm not sure the intuition. I mean, ultimately, I think it comes back to the fact that this is the scaling for the norm that this is in T, it's to the order P plus 1, whereas in W, it's just order 1. And so when you work out the query complexity, when you invert this equation, you end up getting this P root. Not sure I have much intuition behind
Just the less commutative terms.
Yeah, exactly. This commutator scaling is considered good in some sense. And there's this note that I've made at the bottom. People are interested in seeing if they can have the best of both worlds, if they can come up with methods that have the commutator scaling and system size, but they have near optimal scaling in T and epsilon. So people come up with these multi-product formulas where, as I understand it, they're basically doing some kind of extrapolation of the Trotter scheme. And so, yeah, there are papers about that recently. Yeah, not too much of an expert on these, though. I think one thing to point out is that it's a separate point, but although these have optimal scaling in T and epsilon, the prefactor for these can be very large. And so a lot of these methods that have theoretically optimal scaling are not always practical methods. Obviously, qubitization is kind of the state of the art for doing quantum phase estimation, but there, as you know, this is we're not doing time evolution, it's some different unitary that's being implemented. And so this is using qubitization to implement time evolution specifically.
Query complexity per trotter.
Yeah.
How does the cost of every trotter go with P?
Yes, that's with P. I don't think it will depend on P, but the cost of each trotter step should be order n, which I'll try and motivate later when I go through some examples. So the number of gates that you need to implement is going to be at least the number of terms in the Hamiltonian. Number of terms in the Hamiltonian will be order n.
Isn't the second order like you go?
Yes. So this,
it looked like you doubled the number.
Yes. So yeah, you do double the number of terms, and higher order formulas you'll have even more product terms to implement, but this is still order n, right? So you'll just because yeah, you're just running through the terms once and then the second time, so it's kind of 2n instead of
So just 3.
yeah, exactly. So that as you go to higher powers, you have each trotter step gets more complicated to implement, but the error is lower, so there's some trade-off there. And there are papers out there where I've seen people use like the 8th order product formula, but most cases I think the second order is kind of what people work with. Okay. So Any other questions? Okay. So to show, so now to kind of switch directions and talk about how we actually implement this for the Hubbard model. So just to give a little introduction, so the Hubbard model, of course, is a lattice model. Each site on this lattice has one spatial orbital. So if you have a lattice with n sites, then you have 2n spin orbitals in total. And this Hamiltonian has a kinetic energy term, which we call the hopping term, and an on-site interaction term. So this interaction term, whenever you have two electrons, a spin up and spin electron sitting on the same site, you get some energy penalty U. And the hopping term is just nearest neighbor hopping. So it allows hopping of electrons between nearest neighbors on this lattice, but other terms are neglected. So this, of course, is a large approximation. So as I was just saying, there are only order n terms in this Hamiltonian, and the full electronic structure Hamiltonian is n to the 4 terms. And as a point of notation, we can rewrite this hopping term in terms of some adjacency matrix. So this just encodes the connectivity of the lattice. So this is equal to 0 everywhere, apart from elements I, j, where I and j are connected on this lattice. And we also tend to redefine this interaction term. So we replace each number operator n with n minus a half. The reason that this is okay to do, if you look at the difference between the original interaction, sorry, the difference between the two interaction terms, this turns out to be a constant because you're summing over all sites on the lattice, both the spin up and spin down electrons. So this is just the total number operator. And for any eigenstate of the Hamiltonian, the number of electrons is fixed. And so this is just a constant. So if you want to, you can just correct for this afterwards. So if we just look at the interaction term in a bit more detail, so we want to map this to Pauli's using Jordan-Wigner mapping. So here we have that the Pauli Z is 2 times the number operator minus the identity. So now you can see why we want to do this transformation, because this becomes particularly simple. So the interaction term is just a sum over all sites, and then just a product between the spin up and spin down Z Pauli's. And so we want to implement time evolution. So for the interaction term, this is completely trivial because you can kind of see that all of these operators commute with each other, and so there's no trotter error. So any 2 strings of just Z Pauli's will always commute, and so there's no trotter error in this approximation. And so just to note, we can implement a ZZ rotation as in the bottom right corner, a C naught, followed by a single qubit rotation, followed by a C naught. And I was mentioning earlier that trotter schemes are nice because they preserve the locality of the Hamiltonian. So here, each term acts on just 2 qubits at a time, and this is also preserved in the trotter scheme. And so if your qubits are laid out sensibly, then you should be able to implement all of these terms in parallel, right? So this whole step will just be a layer of C naughts, a layer of single qubit rotations, and then a layer of C naughts. Okay, but we want to implement time evolution for the full Hamiltonian. So I've just said the interaction term is straightforward. The hopping term, unfortunately, is less straightforward. So here, each term in a summation corresponds to one of the bonds on this lattice, essentially. So if you're considering 2 bonds that don't touch each other, then these will commute because they act on different sites. Whereas if they touch on the same site, then they won't commute. Still, we can go ahead and write down this formula, this product formula. So this is a perfectly valid thing to do, but this will have some trotter error. And we expect the trotter error here will be relatively large because we're breaking this up into lots and lots of smaller pieces. So how can we do better than this? So firstly, I'll just mention a so-called split operator method. So this was introduced in the paper I was showing at the start by Google and collaborators. So here we just split the Hamiltonian into 2 pieces. We do the interaction term exactly, and then we implement the hopping term exactly. So to implement the hopping term, what we can do is, because this is a kinetic energy operator, this is going to be diagonal in the momentum basis. So if we can find operation to transform from position to momentum, then this will become trivial to implement. So in this paper, they look at 2 different ways to perform this transformation. Firstly, using fast fermionic Fourier transform, and then secondly, using Gibbons rotations. So this circuit is just showing an example of this fast fermionic Fourier transform for an 8-qubit example. And then there are some results, T-gate counts, in the figure on the right. So again, they're looking at 3 different trotter schemes. The first one is fermionic swap, which is something a little bit different. The second one, SO, is a split operator using Givens rotations, and then SO-FFT is using this Fourier transform. And so they see that they get the best results from the FFT method. However, there's a restriction that this only works for square lattices, which have dimension 2 to the n by 2 to the n. This gives the best results, but it's quite restricted. Whereas their approach using Givens rotations is more general, but it gives worse T-gate counts. So then a couple of years later, Earl Campbell put out this paper in introducing plaquette trotterization, or plaque. So here the idea is, instead of implementing the hopping term exactly, we're going to split this into 2 parts, which will be much simpler to implement. So maybe it's hard to see the colors, but you have a kind of a red, what we call a red section, and a blue section. Each of these is made up of these square plaquettes. And if you can work out how to implement the time evolution for these plaquette Hamiltonians, then because these plaquettes don't touch each other, they commute, and so we can implement these individual terms, right? So now we're splitting the full Hamiltonian into 3 parts: interaction term, and then the hopping term into 2. So this is going to have slightly higher Trotter error compared to the split operator approach, but it turns out the circuits are going to be simplified. And this will work for all square lattices. So as I've shown it here, it will work if it's even by even, but you can extend it to work for odd lattices as well. So this brings us on to tile trotterization, which is the approach that we describe in our paper. So this is essentially a generalization of plaquette trotterization, but to work for arbitrary lattices, and also to allow treatment of additional interaction terms, including things like the extended Hubbard model and the PPP model. So to explain how this works, so we're now considering generalized Hubbard models. The hopping term is exactly the same before. We're only considering nearest neighbor hopping. Whereas for the interaction term, here the first term is the usual Hubbard model interaction, but the second term is allowing arbitrary density-density type interactions between any pair of sites and any pair of spins. So for the extended Hubbard model, you just include nearest neighbor interactions, whereas for the PPP model, you consider all n² terms here. Okay, so how can we implement time evolution for this? So actually, this interaction term is no different, because all of these terms still commute with each other, right? Any number operator will commute with any other number operator, and so this is still straightforward to implement. The hopping term, we're going to treat with the same strategy as plaquette trotterization, but generalize this for other lattices. So we say that we're going to split the hopping term into S sections. Each bond on the lattice belongs to one and only one section. And then each of these sections is made up of some number of tiles, or tile Hamiltonians. And so to show some examples of this, the first one I've shown you already. So for a 4x4 square lattice with periodic boundary conditions, we can split it into 2 sections, a red and a blue section, each of which is made up of 4 of these plaquettes, which is a square tile. And then the second example is for a hexagonal Hubbard model, hexagonal lattice, where we split this into 3 sections that we label gold, blue, and red. Each of these sections is made up of 8 tiles. Now these have slightly different shapes. So the key point is that within a section, the tiles never touch each other, and so they always commute. So long as you can work out how to implement time evolution for each of the tiles, then you can implement the corresponding section exactly. And you might ask, can we use any shape tile that we want to try and cover this lattice? And the answer is, in theory, yes, you can always implement a tile Hamiltonian, but some are going to be a lot more expensive than others. And so you want to find a set that is most efficient to work with. And so I'll come back to that later. Okay, so as I just said, within a section, the tile Hamiltonians commute. And so if we can work out how to implement time evolution for these tiles, then this can be implemented exactly. And then we use second order Trotterization. So remember, we run through all the terms forwards and then backwards. So we first implement the Coulomb or interaction term, then all the hopping terms, and then the hopping terms backwards, and then the Coulomb term. And because this is a second order formula, it has the usual scaling that it goes as t cubed. And we have this Trotter error norm that we call W tile that we need to calculate. So the two tasks that we need to solve are, firstly, how do we implement time evolution for these tiles? And then secondly, if we want to do some costing, we need to know how big this Trotter error norm is. So firstly, looking at how we implement time evolution for these tiles. So we can write the tile Hamiltonian like this in terms of this adjacency matrix, R tile. So again, this just encodes the connectivity of this tile. For convenience, we can drop the factor of minus tau and work with this operator m instead. And the way that we're going to implement time evolution for this is by first diagonalizing it. So we can write the adjacency matrix in terms of its eigenvalues and eigenvectors. And so this is a real symmetric matrix, so it has real eigenvalues, and we can choose the eigenvectors to be real. And then we can use these eigenvectors to define this transformation of the fermionic operators. So we define some new fermionic operators B in terms of the original ones A. And then we can write this operator M in terms of these new operators, B dagger B. So to show an example of this, so this is the tile that we were just using for the hexagonal lattice. And note that I've used a very particular ordering here where the first side is first. And the reason for that I'll come back to on the next slide. And we can go ahead and diagonalize this adjacency matrix. And one thing to note is that one of the eigenvalues is 0, and this is actually going to simplify the implementation. And then using these eigenvectors, we can define these new fermionic operators that I call B and C. And then we can write this operator M as root 2 B dagger B minus root 2 C dagger C. And so using this, we can write the time evolution operator. But at this point, you could say that this hasn't really helped us because we want to work out how to implement this as a quantum circuit. So to answer that, we need to find a unitary V which transforms from the one basis to the other. And we need to work out how to actually implement this as a quantum circuit. If we can work out V, then we can just write this line at the bottom. So now the term in the middle is time evolution using the original operators A1 and A2. So it's just A1 dagger A1, A2 dagger A2, which is just the number of operators in the original basis. So these are things that we will be able to implement.
Nick, is there any particular reason 1 and 2 chosen as opposed to 1 and 3? Well, 1 and 3 would be the same, but 2 and 3.
No, it's just labeling. Okay, so the key is that we have to work out how to implement this operator V. So this is perhaps the most tricky bit. This can be done by introducing some fermionic operator Fij. So the action of Fij on AI turns it into AI plus Aj, and acting on Aj turns it into AI minus Aj. So this is actually a fast fermionic Fourier transform for just 2 qubits, it turns out. And if so the slightly tricky thing here is that if I and J are next to each other in the Jordan-Wigner ordering or the fermionic ordering that you define, then this is very simple to implement. It has this matrix representation, and the circuit involves just 2 T gates. So there's no complicated rotations that you have to break down into many more T gates. If I and J are not adjacent, then you could implement this, but it would be a lot more complicated. So to avoid that, we always want to update the ordering before we apply it. So you can update the ordering by applying a fermionic swap operator, which is just a swap gate followed by a CZ gate. So these are just Cliffords. And again, in the usual costing, we just ignore those. And so you can verify that the correct operator V is F23, F12. So you can kind of see this. If you act with F12 on A1, it will give you A1 plus A2 divided by root 2. And acting with F23 will give you the correct eigenvector that you want, A1 plus A2 plus A3 with the correct normalization. And this point about I and J needing to be adjacent is why we chose this particular ordering with one in the middle. It ensures that we don't have to add any more fermionic swaps to achieve this. Okay, so now we have this formula for V, we can plug it in here. Actually, there's one more simplification, which is that these middle three terms, it turns out, can be written as an XX plus a YY rotation. So the circuit elements that we need are implementing this F12 or Fij operator, which requires just 2 T gates. And then the XX plus YY rotation can be decomposed like this. And this uses just 2 single qubit rotations. And importantly, both of these rotations have the same angle. So I was mentioning earlier, can we work with any tile Hamiltonian? And the answer is yes, we can always diagonalize it, but the circuits in general might be much more complicated. And so in our paper, we propose to just use these 4 tile Hamiltonians. So S1, S2, and S4 are types of star interaction graphs. And then C4 is a type of circular interaction graph, hence the naming convention. And each of these can be implemented with just 2 arbitrary rotations, whereas the other gates, like the T gates and Hadamard's, these will increase with the size of this tile. Okay, and just going back, I mentioned this point that the rotations, they have the same angle. But actually, if you're implementing a whole section using the same tile over and over again, what you have to do is implement a whole layer of n rotations, which all have the same angle. And it's the same for the interaction term. Again, it's n rotations, which all have the same angle. And in this case, there's a trick called Hamming weight phasing that we can use to reduce the number of rotations. So this is another approach from the same paper by Google. So I explain this with an example that they give. So suppose we have n rotation gates, all with the same angle. Hamming weight phasing allows us to reduce this to just log n rotation gates by using some Toffolis. So as an example, suppose we want to apply 3 rotation gates to 3 different qubits. We can consider the action on computational basis states. So here, all it will do is add some phase to these. And the phase that it adds will only depend on the Hamming weight. So the Hamming weight of a bit string is just the number of ones in that bit string. So in this first state, the Hamming weight is 0, and it has a phase minus 3 theta over 2. The second 3 states have Hamming weight 1, and it picks up a different phase, and so on. So the idea of this approach is, instead of applying n rotation gates to the system register, you can compute the Hamming weight and apply a smaller number of rotations to that. So in particular, in this case, you can apply Rz theta to the first bit of the Hamming weight, Rz2 theta to the second bit. This achieves the same effect. So it's maybe not super obvious, but it turns out that this is the case. And so in this case, you only save 1 rotation, but in the general case, you go from n to log n. But the catch is that to compute and uncompute the Hamming weight, you need adder circuits which use many Toffolis. So in a general case, you need n-1 Toffolis, and you also need n-1 ancillas. And so this goes back to the questions that we had earlier about how we're costing these algorithms. If you're just counting the number of multiplets, then this is usually beneficial because these rotation gates are by far the most expensive. If you actually want to implement these, then I think it's less clear, because instead of just implementing a single layer of gates, you have to perform these very complicated adder circuits, which can't be parallelized efficiently. So
you're diagonalizing all of these files.
Yeah.
So you're doing one transformation to diagonalize all of them.
Yes, exactly.
And then this Hamming weight computation is essentially classical.
It's
essentially like a classical thing.
I mean, you're still implementing it as a quantum circuit, but this is a trick to, it's just a trick to reduce the number of rotation gates that you actually have to apply.
It's it's like a classical.
Yes. So I mean, I've presented it using computational basis states, but of course this will apply for any state. It's
So the quantum circuit's quite similar to what classical circuit would look like. But for power to computation during the big number, which just have been like.
So yeah, I mean, the circuits that you use to compute the Hamming weight are probably inspired by similar circuits, like classical circuits, where I'm not sure if you've seen these kind of adder circuits. If you want to add two numbers together on a quantum computer, then you have these like Toffoli circuits. So there's probably some corresponding to classical circuits there. But this, I present it on computational basis states, but of course you can take any linear combination and the same argument holds. And so to actually do this, you need to use these ancilla qubits, n minus one of them. So yeah, these are actual qubits that you need.
The Toffoli, there's adder circuits you can do the logarithmic depth, even if you do linear.
Yes, that's true. So I don't know the exact circuit that you need, but I think you probably need like many of these adder circuits in a row. So it's not just one of them. And so
It's only a week on that.
Yes, it's
There is not the long depth implication of you have an ancilla register which has the phase gradient applied to it. The RZ, like RZ. Then you have an AND circuit, which how is it computing how much is it? Is it just applying a Toffoli from your circuit, your state register? What's the
yeah, it's a good question. I admit I have not
Yeah.
looked into the details. I accepted this, but yeah, it's
makes sense. They do both do that a lot with that
Mhm.
phase gradient extra. It only means you have to implement the rotations once, and you can just do other circuits.
yeah, exactly. There have been some other papers recently which propose improvements to this scheme. Actually, so in the paper by Earl, the follow-up to this paper, he proposes some slight improvements to these circuits that, like, if the number satisfies some properties, then you can save a few ancillas and a few Toffolis and these kind of tricks. But I just wanted to present the general idea. This is kind of important for some of the results that I show later when I do some costing. This log term in particular is kind of important to remember.
So why does it have a log? Are you storing the results in a logarithmic number of qubits? And that's why you have a logarithmic number of rotations.
I think the reason it's a log is because you apply the rotations to the bits Hamming rate.
Oh, and you stored, and then you have a logarithmic number of bits.
Yeah. Exactly, yeah. But the number of ancillars, so also relevant for the results later on. But here I'm just saying you do this whole approach to all n rotations, but actually you can also break it up into two chunks of n over 2 or n over 4 chunks. And in that case, you save some ancillars, but you have to do this more times, and so you have more rotations. So there's kind of a way to trade off between the number of ancillars and number of gates, essentially.
Are you doing all your rotations with this strategy?
Yes, yeah. In the results I'll show at the end, we show it without using Hamming rate phasing at all,
Yeah.
and then we show it with different numbers of with layers of size n or size n over 2 or n over 4. So
you just have like a rotation resource, which is adding.
Yeah, essentially.
And that would reduce your T count.
That's right. Okay. Okay. Any other questions? So next I move on to how to calculate Trotter error bounds. So remember, for a second order formula, we have this bound, which we can calculate in terms of this commutator, these commutator expressions. And as I was saying earlier, this is one of the kind of the major problems with Trotterization. Firstly, this might be a loose bound, but even actually calculating this expression can be very difficult in general. So actually, to calculate this, we usually have to apply just a triangle inequality over and over, and you make it even looser. And for very small systems, you can just brute force calculate the Trotter error, but obviously that doesn't scale. Okay, firstly, we can think about the split operator approach. And so this is very simple because here we're only splitting it into two terms. So actually, there are only two terms remaining in this expression. But we want to do this for Tile Trotterization, where we're also dividing the hopping term into S sections. And so I haven't included the proof here for time, but it turns out that the total Trotter error from this is equal to the error from the split operator approach plus the error from splitting the hopping section into many parts. So if anyone wants to see that, I have an extra slide, but it's just a little bit technical. And so for this, the error from splitting the hopping Hamiltonian into many parts, because the hopping Hamiltonian is a one-body operator, turns out there are some tricks to calculate this numerically. So you can write it in terms of the adjacency matrix, which is just an n by n matrix. So even for very large lattices with like 1,000 or 10,000 sites, you can just calculate this numerically. So we've done this, and so this is for hexagonal lattice 3 sections. And so perhaps the most important point here is that this scales linearly in the number of lattice sites. Okay, the more complicated term is this WSO2, as we call it, which again is the error from splitting a Hamiltonian into an interaction term and a hopping term. So we go through the proof of this in the paper, but here I just wanted to sketch the general idea of how you can approach this problem and how you get the scaling of order n. So the key is we need to consider terms of this form, so a commutator between an interaction term and a hopping term, which are going to look something like this. So here you have an interaction term where both of the spin orbitals are different, and you have a hopping term where I and j are also different. So the trick is to make progress, we can note that if all 4 of the orbitals involved are different, then of course these commute because they act on different sites. If both of the orbitals in the interaction term are the same as both of the orbitals in the hopping term, then it turns out they also commute. But if exactly one of them is shared between the two, then the commutator is not 0, but the anti-commutator is 0. And so these top 2 rules can be used to kill off most of the terms, because so if you look at these commutator expressions at the top, because they're at order n terms in HC and HH, you might say that there are going to be order n cubed terms in this, but actually most of these are going to be 0. So if you consider a particular interaction term, there's only going to be order 1 hopping terms that are non-zero, and then there are order n interaction terms. And so that gives us the final scaling that we get here. And I just said that the WH is also order n, and so this whole thing scales just as order n.
Is that because they have to be overlapping?
Yeah,
That's what makes it every site.
yes, yeah, that's right. So again, if you just pick a particular interaction term involving 2 spin orbitals, there's only going to be order 1 hopping terms, which will give a non-zero contribution. Just the terms which where one of the spin orbitals overlaps, essentially.
So we have an identity and then the operator, but it will be expanded out the operator in full over all the qubits again.
Yes, yeah, that's right. And so actually calculating the prefactor for this is quite messy. And as I say, it involves a lot of just applying the triangle inequality, and there are a few other tricks that make this a little bit tighter. So as I mentioned earlier, actually, if you just need to calculate the spectral norm of a one-body operator, of a free fermionic operator, then you can write it in terms of the connectivity matrix, the adjacency matrix. So if you can reduce it to just the norms of one-body operators, then you can do something a bit more accurate. So there are a few tricks like that. Okay. So just to briefly show this slide again from earlier, we're comparing the trotter and post-trotter scaling. So we've just shown that this trotter error norm, WP, is order n. And so we're going to get system size scaling n to the 1 over p. Whereas for qubitization, this norm of the Hamiltonian is necessarily going to go as order n, which is why for lattice models like the Hubbard model, these methods can often win out overall. Okay, so for the final kind of few slides, I'll show an application of this to quantum phase estimation. So far, we've just considered the problem of dynamics, but now in chemistry, we might want to calculate, say, ground state energy or excited state energy. So of course, quantum phase estimation is an algorithm to estimate the eigenphases of some unitary U. Again, in chemistry, we want to know the energies of some Hermitian operator. So the common thing to do is to encode that in the unitary. And so time evolution, e to the minus I of ht, is one way of doing this. So that's exactly what we're going to do here. We'll just take this unitary U as our Trotterized operator. Other choices for U exist. So when we do quantum phase estimation with qubitization, we use a different operator, which is qubitized quantum walk operator. But the idea is otherwise the same. And so in our paper, we do a QP study of tile trotterization for both the Hubbard and the extended Hubbard model on the hexagonal lattice. And then we also do costing of qubitization for just the Hubbard model, but not the extended Hubbard model. Okay, so the results that I'll show are just counting the number of T gates and Toffolis. So just to show the contributions to this cost. So MPE is the total number of trotter steps, which is the number of applications of U. And then for each trotter step, you have to do some number of rotation gates. As I was arguing earlier with Hamming wave phasing, this will be log n. Then for each rotation, this is broken down into some number Cliffords plus T. And then we also have some other T gates and Toffoli gates besides the rotations, which will be order n. So if I go back quite far to look at these tile Hamiltonians, so you have the rotation gates, but we also have 2 T gates in implementing this Fij operator. And then we also have order n Toffolis to do the Hamming wave phasing. So that's the 2 contributions to this term NT. And then the number of applications of phase estimation is a bit more tricky. So delta EPE is the precision from phase estimation that we're targeting. So phase estimation has some finite error to it. I was telling you earlier that the scaling of second order trotterization is T cubed, but that's the scaling in the spectral norm. Here we're interested in calculating the energies of the Hamiltonian, and it turns out that actually here the scaling goes as T squared. So again, I think this is not super obvious, but this is something that you can show. And so if you invert this to get an expression for T and plug it into this formula, we get the following. So in the numerator, you have square root of W, which is going to be order n to the half. And then in the numerator, you have delta EPE, again, is the error from phase estimation, and delta ETS is the error from doing this trotter simulation. And we can do, if we have a target error of, say, epsilon, we can say give half of epsilon to both of these. So both of these are going to be order epsilon, which gets this scaling. So sticking everything together, this is the result that we get. And I leave the log n term in there because this is going to be needed to explain some of the results. And then just in a single slide, qubitization. So I saw you had some previous seminars on this, so hopefully people are somewhat familiar, but essentially we have a quantum walk operator, which can be implemented in terms of these operations, select and prepare. So again, we went through and worked out how to implement these for the specific case of the Hubbard model on a hexagonal lattice. And the main results are that implementing select is order n, implementing prepare is order log L. So this is an L by L lattice. So this is also log n. And so asymptotically, the cost of select is dominant here. And so comparing the cost of these two, and now look at the cost of QPE with qubitization. The number of times you have to repeat the walk operator here is proportional to lambda, which is the 1 norm, which is order n, and it's inversely proportional to epsilon. And then implementing the walk operator, you have controlled select, prepare dagger, and this reflection. So as I was saying, this is order n, and these terms are order log n. So overall, we get this scaling. So this has worse scaling in the system size n, but it has better scaling in the target precision epsilon. And so this is what we call Heisenberg limited scaling. If you want to estimate the energy with some quantum algorithm, this is the best that any method can do. It's the runtime goes as 1 over epsilon. Okay, so to finally show some results so these are for the hexagonal lattice Hubbard model, looking at 3 different approaches. Qubitization is in blue, red is tile trotterization without Hamming wave phasing, and yellow is with Hamming wave phasing using n over 2 minus 1 ancillas. So we were talking earlier about if you have n rotations, you can split this into two. And we're considering two different accuracy metrics here. So on the left is with extensive scaling energies, and on the right is with fixed accuracy. So for something like the Hubbard model, you're often interested in the energy per site. Similarly, for like condensed phase systems, you want to know the energy per unit cell. Whereas, of course, in chemistry, we usually want just like chemical accuracy, which is a fixed target error. But this is epsilon is 0.005 times n, and with Tile Trotterization, it's just a constant. So just going back without having rate phasing, the log n term is not there. And so if we allow epsilon to scale with n, this is just going to be order 1. Whereas with having rate phasing, we have an additional term, which is going to be log n over n. So this produces this slightly strange looking result that actually, as you increase the system size, you need fewer T-gates. But this is ultimately coming from this log n over n term.
The log n plus
Oh,
the log n dominate.
exactly, yeah. So at small system size, the log n over n term dominates, but asymptotically that disappears, and so it just returns to a constant. Yeah, on the right is with fixed target accuracy, and so here qubitization does a bit better. So remember that qubitization has better scaling with epsilon, and so the exact crossover point between these two methods will depend on how you choose that epsilon. But here there's a crossover for like 500, n is 500 or so. And then lastly, to show some results comparing the Hubbard model with the extended Hubbard model. So the Hubbard model is on the left, and we're considering results without Hamming weight phasing, alpha is equal to 0, and then Hamming weight phasing, where we split this into use either n minus 1, n over 2 minus 1, or n over 4 minus 1 ancilla qubits, where again we can split these n rotation gates up into either 2 or 4 chunks. And so I guess the key results here are that in the Hubbard model, the T-gate count is somewhere between about 2 and 10 million, depending on which method you use. For the extended Hubbard model, it's somewhat higher. It's about between 10 and 50 million. So it's about a factor of 5 higher. Most of this additional cost is coming from the higher error norm that we calculate. So each trotter step is slightly more expensive, but that's a smaller contribution. And again, I would note that we can only calculate a bound on these trotter error norms, and so actually the difference between the two might be smaller if you could do better, but we're somewhat limited in this approach. So that would be a nice thing to do in a future study, would be a more rigorous or more careful calculation of these trotter error norms, so that we can see better what the real cost of these methods is. Yeah, so that's something that we're certainly thinking about. Another direction, so again, this costing is just counting non-Clifford gates. Really, if we want to think about actually implementing this on an early fault-tolerant device, we want to actually compile these circuits, work out the Clifford costs, work out what can be parallelized and what can't, and do a more detailed costing. Yeah. Okay, and so that's it. And so my collaborators in Copenhagen. So again, the first author who did much of this work was Andreas. Also Frederick, who's now a postdoc in the US, a maths postdoc. He was in Copenhagen at the time, and Gemma and Solomon. And then from Riverlane, Christoph, who's did a lot of the work on qubitization, and Robert, who's a quantum chemist at Riverlane. Yeah, that's it. Thank you for listening.
That question made sense, but you don't have any error correction in any step, do you?
For these results, yeah, we don't include error correction. So we're just counting the non-Clifford gates, and the reason that we do that is because we anticipate when we apply quantum error correction, these are the most expensive. Yeah, so actually, once you have the T-gate count, so I mentioned earlier, this standard costing model by Daniel Latinsky. which means actually if you know the number of T gates, you can pretty quickly get the rest of it is fairly straightforward. So this is the results I showed at the very start. I can go back. So the results I showed at the start were including error correction to estimate the number of physical qubits and the total runtime, for example. So if you know how many T gates you have to perform, then from that you can work out how many QEC cycles you need to run for. There's a formula that tells you the error rate per QEC cycle as a function of the code distance. From that, you can work out what surface code distance you need, and you can work out the number of physical qubits. So that's the rough idea of how you do this costing. And again, that's just one possible kind of scheme for costing error correction, depending on various things that might or might not be appropriate, but that's kind of the standard in the literature at the moment. And it's the same. Okay, maybe these results don't show it, but many of these similar papers do the same thing.
Can you just go back to the final degree complexity?
Yes.
I missed the last.
I think this one maybe.
Yeah, exactly. Yeah, this. So the last slide, the step from the last slide to this. Can you just go through that one?
So essentially, so you're happy with the number of gates per trotter step. It has the contribution from the rotations. So if you use Hamming weight phasing, this is log n. There's also, I mean, technically the number of rotations, the number of T gates per rotation has some dependence on n, but that's kind of logarithmic, so I'm ignoring that here. The number of NT, you have T gates we have additional T gates from implementing the Tile Hamiltonian and the Toffoli from Hamming weight phasing. So per trotter step, the scaling is order n in total, ignoring the log term. And then
you just group them. Just group them the terms under NP. You combine the constants.
Yeah, so this term is just the scaling for the number of trotter steps. So on the next slide, I group that with the log n plus n on the top.
And when you do reversing.
Yeah. So this is working out how small you need to set t to get your target error. So there's at least two contributions to the error. I'm kind of skipping a few things here. So that the main contributions will be in quantum phase estimation. Obviously, you do it to some finite precision. This is delta E PE. And then in trotterization, there's also an error, delta E TS. And so it's just combining those two. So there's also error from rotation synthesis. And so, I mean, this is basically following exactly the same costing analysis from the Google paper that I mentioned a few times. And Earl's paper also does exactly the same analysis. But in those papers, they go through in a little bit more detail and look at the like the rotation synthesis error, for example. But basically, if we have a target error of epsilon, we can assign, I think they maybe do like a third of that to delta EPE and then 2/3 to the other, or maybe the other way around. But basically, both of these scale with epsilon, so which gets us to the final step.
So the n over 2 is from the square root W.
But
n to the half.
Yeah, the n to the half is because we have in the numerator is square root of W, it's square root of y. Yeah. So this is just multiplying this root n over epsilon to the 3/2 by the term at the top, which is log n plus n.
Yeah, okay. That was it.
Yeah. So,
And I've got one more question. So there's nothing symmetry in the Hubbard model. Particle number, paper spin, for example. Do you think your framework could incorporate that, or?
Yeah. Good question. Yeah, it's not something I've thought about yet. Yeah, I'm not sure how to answer that. But so for qubitisation, for the circuits, there might be ways to improve it using these kind of tricks, I imagine. With the trotterization, I'm not sure.
Nick, when you're making these sort of plaquettes of separate things, you had red and blue ones, and they were sort of set, but that wasn't the only possible set. So when you're doing multiple trotter steps, could you pick different partitionings that look the same effectively? But so you've got the red and blue, but you shove them over by one square, then you've got a different set. Would that change the error bounds in any way? It probably won't change any asymptotics, but it might change some prefactors.
Yeah, it's a good question. I haven't thought about it. So you're saying each trotter step you perform, you just use a different order.
Yeah, different. Yeah, exactly. Yeah, because here there are definitely two. Because you just shoved everything across Fault-tolerant, because then you might couple things differently, and therefore reduce. Allow things to talk a bit more, and therefore reduce any trotter error.
Yeah, that's a good question. I haven't considered it. Like you say, I'm be surprised if it changed things like the scaling asymptotically. Perhaps there are some small improvements. I mean, people do lots of different tricks with trotterization to try and reduce the cost, like people do random trotter formulas. Yeah, I'm not sure. I guess it would complicate the analysis quite well. I mean, I guess in theory, if you're using a different trotter scheme for each step, you can still apply this bound to each step, right? And so it's not obvious to me. And
yes, there might be a correlation from having, if you include two of them together, that would reduce it. But yeah, probably won't change the asymptotics.
yeah, it's an interesting question. Like, as always, like I said already, but this is fairly loose bounds, but also this is just the error in the spectral norm. In some cases, for example, when we were looking at calculating energies, the Hamiltonian at the end, there are different error metrics that you might want to look at. And yeah, in some cases, you might be able to get some clever cancellation of errors, the kind of things that you mentioned. So one thing that we do allow in our scheme is, so in the examples I've given, we just use the same tile over and over again, but in theory, there's no reason that you can't use lots of different tiles. And so actually, we also talk about kind of fragments, non-periodic lattices, and this is a figure from the paper where we show some examples. So this is like a non-periodic square lattice, and there you can use this S1 tile, and we give a Kagome lattice example. So you're using lots of different tiles to cover the lattice, and there's no reason that you can't do this. There are a few considerations, like so actually in the second order formula, the terms in the middle can group together because it's just the same term twice. And so, yeah, actually that's one term that you have to implement fewer times than the other hopping terms. So you can try and play tricks like put more of the trotter error there, or like these kind of things. But again, it's not something we've thought about so far. Like it's the kind of thing that will give you a small improvement, but not like order of magnitude improvement or anything. But yeah, it's interesting to think about.
Random one. These error correction codes typically have these like plaquette type structures. Is there any way you could apply the techniques for like the adjacent to the matrix, like the surface code or something?
Yeah, I'm not sure I can answer.
Sorry, just add this.
Oh, right.
Yeah, it's interesting thoughts. I'm not sure.
Because I've seen like some of these trotterization schemes defined with error detection codes, which have like detection qubits and things.
Yeah.
You can probably define trotterization scheme like yours with those.
Yes. Yeah, that's another thing worth pointing out is I think these trotterization schemes do work quite well with kind of slightly more near-term approaches like error mitigation in particular. There's a paper by Quantinium arguing that actually, like often we assume that if there's even a single error in your circuit, then you have to throw everything away. But actually, in many cases, you can kind of get dilution of errors if you construct the circuit appropriately, especially if you're calculating like a local operator at the end instead of a global operator. In some cases, it's really not that bad. And so you can handle some number of errors, and these kind of circuits might be appropriate there. So that's definitely interesting to think about. Like a lot of the analyses we do, like the QEC costings I showed at the start are kind of absolute worst case. Yeah. But in many cases, you can do better. Of course, people already apply trotterization schemes on NIST devices with very high error rates, and they can still get nice results even to quite large systems using a combination of using things like error mitigation. And so, yeah, definitely in the early fault tolerant regime, a lot of people would think about how you could apply some combination of error mitigation and error correction. I think that should fit nicely into these kind of circuits. And so perhaps another reason that this is a nice thing to think about here.
Right, shall we, thank you very much, Nick.
Okay.